Good afternoon, everyone. Am I audible? So, in the last class, we were talking about the proof of work consensus algorithm. That is, our Bitcoin blockchain uses a proof of work based consensus algorithm for adding the blocks to the blockchain. So, the proof of work consensus algorithm is what uh, allows you to generate blocks in the blockchain. So, technically, what happens is if we have a node on the blockchain, say this node is node A, and this node A creates a transaction. So, it creates a transaction. So, we know the fields that are included in the transaction, and the node A will sign this transaction with its digital signature. Okay. So this digital signature is what allows you to verify the block. That is, the digital signature of the node establishes the authenticity and integrity of the transaction. So remember, when we were talking about digital signatures, whenever a sender signs a transaction or a document with a digital signature, it makes it very easy for the receiver to verify the digital signature. So here also, we make use of digital signatures in order to establish the authenticity and the integrity of the transaction. So we are saying that a node here creates a transaction. It will include all the fields. That is, if a node is wanting to send money to some other node on the network, it will include the version number, it will include the input counters, the output counters, that is the UXTO, the unspent transaction output that the input this node A wants to include, and then it will sign the transaction with its digital signature. Now, after the signature has been done, the transaction goes into a pool which is known as the memory pool or the transaction pool. And here it will include a list of transactions that have been verified but have not been included as part of any block in the blockchain. Okay, so this transaction pool or this memory pool will consist of a number of transactions, and this number can be any arbitrary number. So if you talk about the Bitcoin blockchain, it allows you to add transactions for up to 1 MB, and a transaction is always hashed, so it allows you to add in Bitcoin blockchain, it allows you to add about, say, 1500 transactions in a block. But for our understanding, let us assume that we can add up to, say, 5 transactions in our block. So a node A creates a transaction, it signs the transaction with its digital signature. The signed transaction goes into this transaction pool. Now, we have also talked about, now this node A is creating a transaction. This node is known as a general node. We have other nodes, which are the minor nodes. We have minor nodes. These are special nodes that have the task of generating blocks on the blockchain network. So what happens is this minor node, what it does is it will pick up transactions from the memory pool. The transaction that this minor, we will have some minor, suppose this is minor 1, we will have several minors present. We can have minor 2, we will have another minor which is known as minor 3. So there will be multiple nodes on our Bitcoin blockchain networks that are minor nodes, and we will have several 100,000 general nodes on the network. So general nodes, what they do is they create a transaction, and their transaction is verified using their digital signature, and then it is added to the transaction pool. Now there is this concept of transaction fee. So what happens is, suppose I want to send money, I want to send some Bitcoins to somebody who is on the Bitcoin network and he is present on in some other country, some different geographical location. And I want my transaction to be executed quickly. Now we say that in blockchain, in this Bitcoin blockchain, the block generation time is 10 minutes. That is, every 10 minutes, a new block is generated. So how could you speed up this process? This, you cannot like go beyond this 10-minute time, but what you can do is when you're creating a transaction, you include the transaction fee. Okay. So there is no fixed transaction fee with respect to Bitcoin blockchain network. But what generally happens on the network is that if you include a greater transaction fee, that is, if your transaction has a greater transaction fee, then chances of your transaction of getting picked up for block inclusion is very high. So I'm saying that when you are creating a transaction, you also have to define the transaction fee. So this transaction fee goes to the miner because he is spending his computational power in order to create a block. And when that block is created, only then your transaction gets executed, only then the payment is made. So what this node A wants is that he wants his transaction to be included into a block as soon as possible. So what this node A does is, this node A will include a higher transaction fee. Now, suppose this is transaction 1. This transaction was transaction 1. This transaction 1 has gone inside the memory pool. Now, the miners, when they check for transactions, they always want to include transactions that have a higher transaction fee, because this transaction fee goes to the miner who is successful in creating a block. Okay, so now what happens is we have a list of transactions in the memory pool or the transaction pool, and we have several miners on the network. So miners are block producers. Okay, you can think of miners as block producers. Okay, and they will select unconfirmed transactions from the transaction pool. They will club them, bundle them together, and they will form a block. Suppose we have a miner 1, it selects 5 transactions from this pool, so it decides to select 5 transactions from this pool. So what this miner will do is he will try to bundle up all these transactions. He will bundle up this transaction, that is transaction 1, transaction 2, transaction 3, transaction 4, and transaction 5. So our miner decides to include 5 transactions in his block. Now what will happen is this block is not added to the blockchain. He has only decided to include this 5 transaction in its block. So now this block is known as the candidate block. So candidate block consists of all those transactions that a miner sees fit to include as part of the block. Okay, so our block generation process begins with the miner constructing a candidate block. By candidate block, we mean that the miner will include a list of those transactions that the miner wants to put on the blockchain. Then what happens is the miner needs to calculate the header. Okay, so what will happen is, remember we talked about the Merkle root hash. So what will happen here is we will have transaction 1, we have transaction 2, we have transaction 3, we have transaction 4, and we have transaction 5. So in order to compute your Merkle tree, you will have to calculate the hash of all these transactions. So you pass each of these transactions through the SHA-256 function. You will get hash 1. For this you will get, say, hash 2. For this you will get hash 3. For this you will get hash 4. For this you will get hash 5. Okay. Again, you will perform hashing on pairs. Now, this does not have a like a pair for this. So what happens in Bitcoin is that you will create a copy of this hash and you will hash this. So now our hash is H12. Here we have H34. Here we have H55. Okay. Again, this will be computed. Again, this will be computed. And finally, what you get is your root hash. So this root hash is known as the Merkle root hash. So by having Merkle root hash in the block header, this basically makes transactions tamper proof because you are passing your transactions through the hash function to get a root hash which is known as the Merkle root hash. So you use all these transactions and you pass them through the hash function to multiple times in order to get a Merkle root hash. So now what you will do is you will use the Merkle root hash. You will use the last added block to the blockchain. So we have a blockchain, say this is our blockchain, which consists of a series of block and every block is linked to the previous block. Okay. So every block has a block header. This block will have a block header. This block will also have a block header. Here also we will have a block header and this block will also have a block header. Okay. So what this miner will do is miner will pick up some transactions from the transaction pool to include it part of as it like part of its block. He will perform the SHA-256 function on it repeatedly in as soon as he gets the Merkle root hash. So he has to hash these transactions in order to get the Merkle root hash. So he will include the Merkle root hash. He will use the latest block header. He will use the block header. He will also include the difficulty target, which has been determined, which has been designated by the Bitcoin protocol. So he will use all three of these things. He will use the Merkle root hash. He will include the block header of the latest block in the blockchain. And he will use this difficulty target, which has been defined by the Bitcoin protocol. This is difficulty target. Sometimes it is also known as the difficulty parameter. So these are the things that is available to the miner. So now what miner does is that we are saying that he needs to solve a cryptographic puzzle. So this difficulty target is the cryptographic puzzle. So what our proof of work algorithm says is that whenever you want to create a new block in the blockchain, you will have to ensure that whatever hash you get, that hash has to be less than the difficulty target that has been determined by the network, that has been set by the network. So the reason that this Bitcoin protocol does this is your proof of work that you need to do. That is, you need to use your computational power to like give a proof that you have done some amount of computational work in order to prove that the hash of your new block is less than the difficulty target. And when you perform this proof of work, when you perform this computation, this cryptographic hash functioning, you will take around 10 minutes to solve this. Okay. And this 10-minute is also known as the block generation time. That is the difference between two blocks that are generated. So in every single block, we have a value that is given by the like your Bitcoin protocol, which is known as the difficulty target or your difficulty. So this difficulty determines how difficult it is to get a hash which is less than the difficulty target. So now what you do is you take your Merkle root hash, you take your block header, and you pass it through a cryptographic hash function. So what I'm saying here is that you take your Merkle root hash, you will take the block header of the previous block, the block header of the previous block, because you are chaining your block to this block, because you need to form a chain. So in order to add a new block, you will have to link it to the previous block, which is why you're using the block header to the previous block. So these two parameters you need to pass through a SHA 256 function. So you're passing through two parameters through this SHA 256 function. And when you pass something through an SHA 256 function, you will get a 256-bit hash value. And this 256-bit hash value should be less than the difficulty target set by the network. Okay, so this is the proof of work that you will have to present every time you want to add a new block to the chain. Now what actually happens is, we have already studied about the SHA 256. So we are saying that whenever you pass something through an SHA 256 function, you will always get the same value. So for example, if I pass hello, I will get a 256-bit value, which will be a combination of some 256 bits. So no matter how many times I pass this hello through this SHA 256 function, I will always get this value. So similarly, if you're passing this through SHA 256, you will get the same bit value, same hash value, no matter how many different times you pass through it. So your hash value will not change every time you pass through it. So what we need to do is, we need to add a number which is known as the nonce. Okay. So what we are saying here is that whenever you pass something through the SHA 256, you will get a 256-bit hash value. And this 256-bit hash value should be less than the difficulty target which has been set by the network. Now, if you only pass these two parameters through this SHA 256 function, you will every time get the same value, because you are passing the same input through the hash function. So we know that our hash function is deterministic, so we will get this same value. So now what we need to do is, we need to find this number nonce. We need to find this number nonce. So nonce, what it does is, your difficulty target has been given to you, that this is the difficulty target and your hash should be less than this difficulty target. And your difficulty target has a number of leading zeros and 1. Okay. So now what we do is, in each iteration, we try to change this bit with zeros and ones. So if we have a number of leading zeros, so we try to change this bit to 1. So if you change even a single 0 to 1, your hash will change. So what you will do is, you will pass this hash function through this SHA 256 by changing this number of leading zeros using this nonce, and you will have to pass this hash value, you will have to pass this input through your hash function millions and millions of time in order to get a hash which is smaller than the difficulty target. And if you find a 256-bit hash value which is less than the difficulty target, then you have found the next Bitcoin block. And as soon as you find the hash value that is less than the difficulty target, which means you have created a block, you will digitally sign, you will put your digital signature on the block, the miner will put the digital signature on the block, and it will broadcast the block to all the participants on the blockchain. Now what will happen is every participant on the blockchain will propagate this block and verify the digital signature and the difficulty target. And once this has been verified, you are allowed to add the block to the blockchain. So this is the proof of work concept that is used. Yes, you need to change the nonce value in each iteration. So basically, the concept here is that whenever you are trying to get a new hash value, you cannot get it because you are simply passing your Merkle root hash and your block header through the SHA-256 function. And this will always give you a constant value, because since you're including some transactions and since you're using the previous block header, those are constant values, and no matter how many times you pass it through your SHA-256 function, it won't change. So what you need to do is you use a parameter which is known as the nonce value. And this nonce value allows you to bring randomness into the input that you're passing through the SHA-256. That it is a number which is added to the input which is to be hashed, which allows you that you rehash your value every time to get a number which is less than the difficulty target. So nonce is the number that the miners are actually solving for. And nonce actually means number only used once. And whenever you find that nonce, because you're changing the number of ones that you are adding, that is like you're changing the number of ones in the leading zeros. So this number of ones, whenever you find that exact number of ones that brings your hash value to a number less than the difficulty target, you have found your new block. So this is actually how the process of Bitcoin mining works in blockchain. So to summarize, what you actually do is each of the miners will collect transactions from the transaction pool. He will use his computational power, whatever CPUs or GPUs or ASICs unit it has available with him, and he will try to generate a block by repeatedly passing some parameters, that is the Merkle root hash, the previous block header, through the hash function. That is, you are repeatedly invoking the hash function on the Merkle root hash and the previous block header. And the data that you are including as part of your block are the transactions that you want to include. You will include the hash of the previous block. You will include your public key address, and you will include a nonce. So when a miner is when a miner is like successful in generating a block, it means that the hash of a block has like a hash value which is less than the difficulty target. And then she will broadcast her block to the network. And other miners, what they will do is they'll verify that block, that is, they will check the miner's digital signature, and they will extend the blockchain from this new block only if they find that this block is valid. That is, it refers to the previous block on the longest chain and it meets the current difficulty target. So when the miner is successful in creating a block, he will get a block reward. That is, he will bring new bitcoins to the system, and also he will be rewarded with the transaction fee that every like transaction initiator, like you and me, we created a transaction, we included a transaction fee. That fee will also go to the miner. And we have already seen that the difficulty level is adjusted every 2 weeks so that the block gets generated once every 10 minutes only. Now, today we will see some important concepts associated with the Bitcoin. That is, whether or not any kind of attack is possible on the Bitcoin. Okay, so Now, let us talk about this concept, which is known as the longest chain concept. So, suppose we were talking about the miner getting a hash which is less than the difficulty target. Now, it may also happen that two miners generate the block at the same time. That is, if I am a miner, I include some transactions in my block. I include the previous block header. I generate a Merkle root hash. I get a a hash value which is less than the difficulty target. At the same time, there was another miner who was using his computational power. He included some transactions and he was repeatedly trying to invoke the hash function on its input to get a hash less than the difficulty target. So what will happen if we get two blocks at the same time? Now we will allow the both the blocks to be added to the blockchain. Okay. And whenever there arises a situation when two miners get blocks at the same time, then mostly forking will occur in the system. So by fork, what we mean is when forking occurs in our system, what we mean is, so you can see here that previously we were having a single chain on the network. At this point in time, two miners create blocks that they were able to solve the cryptographic hash puzzle at the same time. So they created two blocks here. Now what will happen is nodes will adopt the concept of longest chain. So what they will do is both of these blocks refer to the same previous block. Now the miners can continue to build a blockchain either on this block or this block. Okay. So they can either follow this chain on the blockchain and they could either follow this chain on the blockchain. Okay. So whichever chain is the longest, that is, whichever chain has the highest amount of proof of work done on it, that chain will be used as the chain in the blockchain. So the longest chain actually represents the total amount of computational power that has been spent. So obviously, if miners are spending a lot of computational power, that is, they're spending a lot of time doing the proof of work and adding blocks to the blockchain, then that will obviously signify that larger or greater number of blocks have been added to that chain. So what actually happens on the network is both these chains are allowed to extend. Okay. But at some point in time, there will be a chain that will be the longer chain. And the Bitcoin protocol signifies that whenever you get a chain that is a long chain, that is the longest chain, you will only add blocks to that chain on the network. So what actually happens here is if two blocks are generated at the same time and they both refer to the same last block, so we are having two branches here. We have two branches that has emerged from the same blockchain. So this Bitcoin protocol, it needs to resolve this. So it employs just one single rule. It lets the branches grow. Okay. It will not do anything. It employs one single rule that it will allow both the branches to grow. But as soon as one branch grows longer than the others, specifying that that branch has performed larger amount of proof of work, all miners that are present on the Bitcoin blockchain, they need to switch to that blockchain. So here we allowed both these branches to grow. So your Bitcoin proof of work consensus has one simple rule: you don't do anything, you allow both of these branches to grow. But as soon as one branch grows longer than the other branch, it signifies that you will have to, it dictates that you will have to move to the longest chain on the network. So here, whatever blocks have been present on this blockchain, whatever blocks, here we have two blocks, and these two blocks will have, like, will be including some number of transactions. So these two blocks will be discarded, and the transactions that were present in these blocks, they will be reversed. Okay. And we will again have a single blockchain. So there is one rule on the Bitcoin blockchain, that even if your block is added to the blockchain, that is, your transaction has become a part of a block and it has been added to the blockchain, you should not consider your transaction confirmed. You should only get, like, consider your transaction confirmed when six blocks have been added ahead of your block. So what I'm saying here is, say you have a blockchain. So this was your blockchain, and this is linked to the previous block in the chain. And suppose a new block is added to the blockchain, and this block contains your transaction. Say your transaction was transaction 100. Okay. So it will include many other transactions, but it also includes your transaction. Now, even though this block has been added as part of the blockchain, you should not consider your transaction confirmed. You can only consider this transaction confirmed when a total of six blocks have been added ahead of your block. Only when six blocks have been added ahead of your block, which contains your the transaction, only then can you consider your block confirmed. Because it may always happen that two blocks may have been added at the same time, and then the network will see which chain grows the longest. So if you happen to find your transaction on this blockchain, then obviously when this chain grows longer, this will get discarded. So the rule of thumb here is that you will only consider your transaction present inside a block confirmed when a total of six blocks have been added ahead of it. Okay. So this is the concept of the longest chain. Now we have an attack which is known as the 51% attack. That is, can you rewrite the blockchain? So by 51% attack, what I mean to say is that you have 51% control on the network. So here, our Bitcoin network is a peer-to-peer network. Every peer is making use of its computational power to, like, create a new block, add a new block to the chain. But if you are able to control 51% of the Bitcoin blockchain, we need to see what will happen. So what I'm saying here is that if you're able to control 51% of your network, that is, you're controlling majority of the network. And when you're controlling majority of the network, you are also controlling majority of the computing power that is present on the network. So this 51% attack is also known as the majority attack. And as I've been saying previously, that the nodes will always move to the longest chain on the network. So what if you have 51% power on the network and you are able to create a chain that is the longest chain? That is, you are controlling, you are hacking the network, you are creating a blockchain that is the longer version, and the Bitcoin protocol requires that the nodes will have to accept the longest chain that is present on the network. So let us see what this 51% attack is. So a 51% attack refers to the act of intentionally building a new longest chain and you are replacing the honest chain, that is the valid chain. So I'm saying that if you control 51% of the computing power, or if you're controlling the majority of the computing power on the network, you are building a new long chain that is replacing the honest chain, because your protocol requires you to accept the longest chain as the valid version of the Bitcoin blockchain. So, if you are building a dishonest blockchain because you control 51% of the power, then what will happen is the previous blockchain that consisted of all the honest, valid, verified transactions, they would be deactivated because it would no longer be the longest chain, and it will deactivate your blocks, and chain reorganization will occur, and your chain, the dishonest blockchain, will become the new longest blockchain. So let us see how this actually happens. So here you can see that we have some number of blocks present on the blockchain. Okay. So here in the first blockchain, the one in the green color has honest miners that are working on it to create blocks. So we have block 38, 39, 40, 41, 42. So these miners are adding blocks to the chain, and they're also broadcasting them on the network. Now, meanwhile, what happens is that whenever you find a new block, so this is a peer-to-peer network and you're always propagating transaction, you need to propagate transaction on the network. So we are saying that whenever a miner finds a new block, they will have to propagate that block, that is, they will have to broadcast that block to all other miners so that they can verify whether or not the block needs to be added to the blockchain. Because one process is creating a block, another is verification. Now here we have this corrupt miners. So this is the honest chain. It consists of some truthful miners who are mining the blocks, and they are broadcasting the block on the public chain by broadcasting these transactions so that all other miners can verify whatever blocks are being generated. So here we are creating a honest blockchain, and we have truthful miners who are adding the blocks. Now, here we have this corrupt miner who is busy creating a new blockchain. Okay. And we are assuming that this miner has 51% control on the computational power. So we are saying this miner has so much computational power present with him that he is able to generate new blocks. But what this dishonest miner or this malicious miner is doing is, even though he is creating the blocks, he is not broadcasting the solutions on the honest chain or the public chain. He is not broadcasting the solutions to the rest of the network. And since he is not broadcasting the solutions, no other miners have idea that this blockchain also exists. Okay. So the scenario what here happens to be is, we have two versions of the blockchain. One version that is being followed by uncorrupted truthful miners, and the other one that is followed by this corrupted miner. Now the corrupted miner is now working on his own version of the blockchain, and he's not broadcasting it to the rest of the network. And the rest of the network does not pick up this chain because, after all, it hasn't been broadcasted. This chain is isolated from the rest of the network. Okay. Now, let us assume that this corrupted miner, he has, say, some amount of bitcoins with him. Say, suppose he had 100 bitcoins with him. Okay. So let us assume that this miner, this malicious miner, spends his digital currency, that is, he spends his 100 bitcoins on the public chain, and he buys himself a car. Okay. So we are saying that the corrupted miner spends his digital currency on this honest blockchain, the truthful version of the blockchain, that is, this blockchain in which all the truthful miners are working on. and he spends this currency to buy a car. So when you look at here, you can see on block 40 that he has spent his 100 bitcoins. Okay. But when he is creating his dishonest blockchain, he does not add that transaction. So on this truthful, honest blockchain, his money is spent. But meanwhile, he does not include that transaction on his isolated version of the blockchain. On his isolated version of the blockchain, he still has the digital currency. And at the same time, what he does is he still keeps on picking up transactions, forming them into a block, and keeps uh, creating a isolated version of the blockchain. Now, the truthful miners, they are adding blocks to the blockchain, but they are doing it as at a slower pace. Why they are doing it at the slower pace? Because they are broadcasting their transactions. They are broadcasting whenever a block has been created, that block is being broadcasted to all the miners, all the nodes present in the network, so that they could add that block on their blockchain. But here, this dishonest miner, he keeps creating a blockchain. He verifies that blockchain, but he's not broadcasting. And since you're not broadcasting your blockchain, you are saving time. So the scenario here is we have an honest blockchain, a dishonest miner spends his money on this honest blockchain, but in his blockchain that is the isolated blockchain, he does not add this transaction. So on his isolated blockchain, he still possesses 100 bitcoins. Okay. Now, what happens is the truthful miners are adding blocks to the blockchain, but they are adding them in a considerably lower pace than the malicious miner. Also, the reason is because they have lesser hashing power. Why they have lesser hashing power? Because they control only 49% of the blockchain, while this miner controls 51% of the blockchain. So what this malicious miner is trying to do is he's trying to create blockchain at a faster pace than the honest blockchain. He's trying to catch up with the public blockchain. Okay. Now, as soon as the corrupted miner creates a longer blockchain, he suddenly broadcasts this version of the blockchain to the rest of the network. Okay. So now what he does is he will broadcast this blockchain to the rest of the network. Now the rest of the network will detect that this correct version of the black blockchain is actually the longer version than the one they were working on. So now the miners realize that the version of blockchain that they were working on is not the longest, whereas this blockchain that has been broadcasted is the longest version of the blockchain. So now the protocol forces them to switch on to this chain, because the Britcall protocol states that you will only work on the longest possible chain on the network. So now what happens is this malicious miner has broadcasted his longer version of the blockchain to the rest of the network, and the protocol forces even the honest miners to switch onto this blockchain since it is the longest blockchain. So this old public chain is now abandoned because this is shorter, and all the data that is present on this blockchain becomes irrelevant. Now you can see here that this malicious miner is still in control of its 100 BTC. Even though he spent his 100 BTC on the honest blockchain to buy a car, he did not include this transaction here. And since in this transaction he still says that he hasn't spent any BTC, he still has his 100 BTC, then what happens is even though he has already spent it, he still has those 100 BTC. Now, the malicious miner is once again in control of his 100 BTC and he will be able to spend them again. So this problem is known as the double spending problem. That is, double spending problem refers to the problem of being able to spend your currency more than once. So, double spending is a phenomena where a single unit of currency is spent more than once. So, this will create a kind of disparity in the spending record and the currency that is actually available. And this double spending problem is most commonly associated with digital currencies like Bitcoin and Ethereum because digital information is easier to reproduce or manipulate. Okay. So the question here arises then that how easy or difficult it is to carry out the 51% attack. So, like the scenario that was presented here, the miner was able to control the 51% network. But in reality, how difficult or easy it is to control the 51% networking power. Now we are saying that in order to do a 51% attack, or in order to double spend your currency, to spend your currency more than once, you will need to get all the hardware needed in order to perform the attack in the first place. You will have to acquire like so much hardware that it would be incredibly expensive and difficult, because you need to replace majority of the network, and the Bitcoin network contains about like millions of nodes. So even if it has 1 million nodes, you will have to control at least more than half a million node in order to perform this kind of attack. Okay. So acquiring that amount of hardware would be incredibly expensive and difficult, because you will have to replace majority of the network. However, if the attacker does manage to acquire a majority of the mining power, then it is only a matter of time before he can build a new longest chain. But having said that, it is more difficult to replace large number of blocks than it would be to replace just a few. So say that right now, at this present moment, some 3 lakh blocks have been generated. Okay. In order to create your longest chain, you will have to create more than 3 lakh blocks. And for solving for those 3 lakh blocks, you will need to create blocks more than 3 lakhs. And also for solving 3 lakhs block, you will need a lot of computational power. So if you needed to replace about 100 blocks, that wouldn't have been a problem. But now if you need to replace about 3 lakh blocks, that is not an easy task. You will not be able to create a chain longer than the one that consists of 3 lakh blocks. So the further down a transaction is in a blockchain, the more time and energy it is going to take the attacker to reverse it. And so with so many limitations, as of now, a 51% attack has never been carried out on a blockchain. And the proof of work consensus mechanism also limits the chance of any kind of attack like this 50%, 51% attack to be done on the blockchain. Now, there's just one thing that is remaining, which is the security of the blockchain network. So there are 4 things that we are talking in terms of Bitcoin security. One is authentication. So you can ask the question that, am I paying the right person? I don't want to pay some impersonator, because you want to ensure that you're sending Bitcoins and you want to ensure that you're paying to the right person on the network. So authentication is established with the help of public key cryptography. That is, you're using digital signatures. So authentication and integrity can be established with the help of digital signatures. And also, since you are including your unspent transaction output, and the unspent transaction output dictates that the Bitcoin database will allow you to add only those Bitcoins that haven't been spent till now. because whenever you are spending your Bitcoin, you will have to unlock them to spend them. So every time you do a spend, a lock or an unlock, a transaction, a UTXO has been created. So authentication and integrity is established with the help of digital signatures, your cryptographic hash, and your unspent transaction output. Then we have a question: is the coin double spent? So, this we have already discussed that is it possible to double spend your coin? Also, can an attacker reverse or change transaction? We have also discussed about this in the 51% attack. Then, availability. Can you make a transaction anytime you want on the Bitcoin network? Yes, of course, you can make a transaction anytime. The time for your transaction to get committed to be added on the blockchain varies a lot. It may either take a day, two, 5, or even a week for your transaction to get confirmed. Then, confidentiality. Confidentiality is also provided by the Bitcoin network, but it is not complete anonymity, it is pseudo anonymity because you are linked to your Bitcoin address. Even though you're not using your personal name or anything associated like your like your identity, a government identity, you're still using your digital identity, you're using your Bitcoin address, public address. So it is kind of pseudo anonymity, and your transactions, even though they are present on a public blockchain, they cannot be traced by you or by some government agency. So this is one, like, if you talk about this pseudo anonymity concept, so a lot of Bitcoin is being used on dark web, and the reason for happening so is because your transactions are not traceable. A lot, like, previously there was news on the internet that ISIS is buying a lot of weapons using Bitcoins because your transactions are not traceable. You are provided with pseudo anonymity. You, like, I can know that this Bitcoin address is being used for transferring money or for money laundering or for say buying weapons, but you cannot know which person does this Bitcoin public address belongs to. So these are some advantages as well as disadvantages associated with Bitcoin. And we've already, now if you talk about double spending, how could you not double spend a transaction? So since your Bitcoin blockchain consists of a history of all the transactions present, and each node, before like adding a transaction to the mining pool and even adding that transaction into the block, they first need to verify how that transaction, from where that transaction is coming from. That is, they are checking the unspent transaction output. So if I am saying that I want to spend those 5 Bitcoins, I will also have to give a track of how I had those Bitcoins. That is, I have to have a kind of a bank statement that is provided by my unspent transaction output. So the miner is able to verify, or even another node is able to verify that this is my first spending of the Bitcoin as a pair. So this is how you prevent double spending. Next, we see that reverting is hard. We have already talked about this, that as your chain grows in size, it is easy to reverse one or more of the transactions. But if you modify even a single transaction on your blockchain, you will have to recompute the nonce value. And recomputing the nonce value is very difficult because you have to hash and rehash your entire block through the hash function millions of times. And it may take about 10 minutes to get one block. Imagine changing 3 lakh blocks. Okay. So reverting a transaction is very hard because your chain grows in size. You have to recompute the nonce every time you want to change any transaction on the blockchain. So reverting is very hard on the blockchain. But we have some practical limitations. That is, it takes around 10 minutes to verify a transaction. You have to wait for one block, that is 10 minutes for the transaction to go through. But if you are performing a transaction of, say, thousands of dollars, you will have to wait longer for it to become more secure. So for larger transactions, you will have to wait for 6 blocks or 1 hour to get your transaction confirmed. So this is the practical limitation. Then we have already talked about optimization. So Merkle tree is a space saving technique which is used in Bitcoin. What you're doing is you have several transactions here. You pass them through hash function. You hash them and rehash them until you get the Merkle root hash. And this Merkle root hash, along with the previous hash and the nonce value, is what is passed through the SHA-256 function to get your hash value which is less than the difficulty target. So what we are saying here is that in when we're performing a proof of work function, we only keep the root hash. We delete the interior hash values to save the disk space. And the block header will only contain the Merkle root hash. And each block header is about 80 bytes. So 80 bytes, one block header is 80 bytes. We create 6 blocks per hour. We have 24 hours in a day and we have 365 days. So you're only consuming 4.2 MB each year when you're using Merkle tree. And this is a space saving technique which is used in Bitcoin. Then we are talking about simplified payment verification. So since we are hashing transactions and Merkle tree is a form of you can say a tree which allows you to also verify transactions. So if you want to verify a transaction, say TX3, you do not have to go through the entire number of transactions present on your block. You will only need to go from this transaction to this hash 23 and then to the Merkle root. Okay. So you do not have to go through the entire list of transactions since it is not present in the form of a list. It is present in the form of a tree. So verification of a transaction present inside a block becomes very easy. And finally, we have a summary here for the Bitcoin network. We have peer-to-peer nodes, and every new transaction is broadcasted to all the nodes. The transactions get collected in the memory pool, also known as the transaction pool. The miners collect new transactions into a block, and the miner nodes need to find a proof of work. The one to finish the proof of work first probably wins. When a node finds a proof of work, it will broadcast it to all other nodes. The nodes will accept the block only if the transactions are valid, that is, they check the digital signature. And they also check the transactions, that is, those transactions have all not already been spent. So you're checking the unspent transaction output. And the block is added using the hash of the current block to the blockchain. So you're using the hash of the previous block to link your current block to the blockchain. So we'll stop here. This completes your Bitcoin network. If you have any doubts, you can please ask. I don't have time left now, but in the next class, I would like to do a quick demo to show you at least some of it, how it functions. So if you have any doubts, please do ask, and otherwise we can end the class here.